Here's my tutorial on Lewis structures. Intro. I won't be pausing for you to think, because I don't know how much you need to think, so hit pause when you need to, go back, rewind, I'll never know, it's okay. Have a good think, try some on your own. When I start to try one, hit pause, take yourself a little quiz, see if you got it right. I would copy this down somewhere. The octet rule, it's not really a rule, but people say that, is that atoms want to have 8 valence electrons, and hydrogen, though, only wants to have 2. And covalent bonding is sharing a pair of valence electrons, and that's one of our little symbols for electrons is E minus, because they start with E and they're negative. So hit pause, write that down. So let's do some samples. And there are some exceptions to the rule and some weirdness, and we'll get into it. So H with F, and we're gonna make a covalent bond, and that's a shared pair of electrons. Grab your periodic table. H is in your 1 valence electron column. Remember, it goes 1, 2, well, these won't come up, but 2, and 3, 4, 5, 6, 7, 8 valence electrons. Well, these won't come up either because they don't do anything because they're the noble gases. And because they already have 8 valence electrons, they don't want to participate in any reactions, including these. So it won't come up. But hydrogen is in our 1 valence outer electron. That's something that has 1 outer electron in its outer energy shell or level. And fluorine has 7. And also the valence counting I just did pretty much only works to the bottom of the stairs. So let's not say, oh, so lead has 4 valence electrons. First of all, lead wouldn't come up in these problems because we're going to use the nonmetals and the metalloids maybe. But also it doesn't really work down under these shaded boxes. It kind of works for aluminum. That's why I said under the stairs. It only works at the bottom of the stairs, like aluminum, germanium, and so forth. So fluorine has 7, hydrogen has 1. So let's write those in. Now, there's going to be a bond, because that's what we're talking about, right? And a bond is 2 shared electrons. So if you start writing your dots, your shared, your valence electrons, just anywhere, you end up with a lot of erasing. So let's try to use our brains ahead of time. And I'm going to have to share a pair of electrons, and probably many times one from each. Let's plan ahead. Let's take that single one from hydrogen and aim it at fluorine. And then fluorine has 7, and they tend to be in pairs. And I know somebody will say, but you said they're negative, and negative repels. Yes, but they also tend to travel around a single atom in pairs. So that actually is one of the sort of necessary things. And on the AP test, for instance, they mark you off if you don't put them in pairs. So fluorine has 2, 4, 6, and a 7th one. And any bond is a shared pair. So what we usually do is illustrate a bond with a dash, and the dash means 2 electrons. So look, these are shared. So the next thing, though, is that both of them view the bond as belonging to themselves. So if we sort of Venn diagram this, what we get is hydrogen says, I own this pair, and I have 2, and that's what I said it was looking for, 2 valence electrons, so it's satisfied. And fluorine says, I own the bond and all the unbonded, or lone pairs, and I have 2, 4, 6, 8, and it's satisfied. The circles are not a requirement of the diagram. Pretty quickly, you probably start just doing that mentally, but I thought I'd show you. So how about number 2, NH3? Now, the single one will go in the middle, and the others are arrayed around the outside, and we'll probably spread these out just to get some room. Sometimes you see a kid put all 3 of them at the top, and for the intro level, right now, I don't want to argue about the shape. That's for another time. I'm just trying to get some room here. And H, we said, has 1 valence electron. And how about we aim it at the end, because I bet I have to share those. So let's not put them somewhere else so that we have to erase them. And nitrogen has 5 valence electrons. Remember 3, 4, 5, 6, 7, 8, so 5. And you know what? Let's use 1 here and make a bond, and 1 here and make a bond. That's the second one. And the third one and make a bond. And somebody is now yelling at me in the brain, but you said 5. You're right. I only used 3 from nitrogen, and they were 5, so I get 2 more, and they stay on nitrogen. And you'll see people do a number of things. They might draw a little line. But what I think is most useful for upcoming quizzes and notes and so forth is if we make a little cloud on the center one and put the 2 electrons in there. Some people won't draw the cloud on the center one, and it's not necessary, but it will become more useful when part of the quiz incorporates, hey, what shape is this? And the cloud is more informational in a way. So I'm suggesting that we start doing that, at least for the center lone pairs on the center atom. And then we could double check ourselves. Hydrogens say, I own this bond, I have 2. And the nitrogen says, I own 2. Remember, this pair just belongs to nitrogen, 2, 4, 6, 8. And it has its octet, and it is satisfied, and that's it. That's that molecule. And by the way, that's ammonia that you clean up the kitchen with. It does a pretty good job of cutting grease. How about this? And this is methane that comes out of your stove, assuming you have a gas stove, or it's mostly what comes out of the stove. Oh, and by the way, it doesn't stink on its own. They put the stink on that to warn you that the gas is on. Anyway, we said the single one will go in the middle, and the others are arrayed around the outside. And hydrogen has 1 valence, we remember hopefully by now. And let's aim them toward the center, I think. And carbon is in our 3 valence, 4 valence column. And look how many bonds we have to make. We have 4 bonds to complete, and I have 4 electrons left over, so that matches up really well. 1, 2, 3, 4, and that's it. If you draw those little circles that we talked about before, like this one, I think you'll find that the hydrogens view themselves as having 2 valence, and carbon views itself as having 8, and that's done. I'm going to say hit pause and try NF3 because it's a lot like one of the ones we already did. Okay, you're back. N goes in the middle, and the fluorines are arrayed around the outside. If you check your periodic table, N is in the 5 valence column, and F is in the 7. Now, everybody gets a little tired of all these dots, so I'm going to show you another little sort of trick. It's a very allowable trick. They allow this even on the AP test. So I didn't make this up. It's not just mine, and it's very, very accepted, which is to skip writing all the dots and just go 2, 4, 6, 7. So a line is 2 electrons, even if they're not bonded. 2, 4, 6, and I bet that 7th one has the aim in the middle because the single ones usually get used for bonding, and sometimes the other ones, but especially the single ones. 2, 4, 6, and 7. And nitrogen brings in 5. So I need 1 for here, 1 for here, 1 for here, and that's a total of 3. And again, a lot like this one, look, I have 2 left over. And how about we put it in a little cloud there, because later on we'll talk about how much space things take up. And if I draw it as a cloud, it's going to be more of an illustration of the space that that cloud takes up. I'm going to go to number 7. And here we're going to get a little bit more tricky. O and O. And oxygen is in my 6 valence electron column. So I'm going to use the bars now, the lines. And I'm going to go something like 2, 4, 6, 2, 4. And I know there's got to be a bond at some point, right? So how about I borrow from one of these and I put it in here. Now you may have had a teacher who said, no, you take 1 from the left and 1 from the right and so forth. And you can get the right answer that way, but we don't know where electrons come from. They're all perfectly identical. We have no idea how they traveled to where they are now or where they came from. So I'm not cheating by taking the ones I want to move and putting them where I need them. And if I just follow all the rules, I'll get the right answer. And I erase less than the other methods I was mentioning. So I haven't cheated because I have a 6 valence and a 6 valence. And that should mean I have 12 illustrated on the paper, right? 2, 4, 6, 8, 10, 12. So I haven't moved anything off the paper. I haven't moved anything in illegally. I still have 12. I just moved where they are in the molecule. But I'm not done, because if we mentally diagram this one, it's 8 valence, and if I diagram this one, it's 6. Well, oxygen's too attractive to electrons, and it's not going to sit there and take it. It's going to get grabby. And the right one is unhappy with 6 valence, so it's going to grab one of the pairs from the left side. It doesn't really matter which one, and in fact, you might remember that none of these pairs are sitting there just on the top or the left or the bottom or anything, because all electrons are in a hugely fast rush of an orbital around the nucleus. So, you know, our illustration of them being at the top is completely wrong. So wherever you put them, they're not really there. It's just a way to keep count, really. So pick a pair Maybe we'll choose the bottom this time just because I left the bottom blank over here. Maybe it looks better if they match, but it doesn't really matter. And I'm going to borrow that pair, that one this time, and I'm going to pull them in here. And again, the count remains the same. I just moved them. But the point is here that now the right side borrowed from the left into a bond, and now they both Venn diagram as having 8 valence electrons. And as you probably know, that's probably the second most commonly known chemical formula after water, and that's oxygen in the atmosphere. So the stuff you're breathing and metabolizing in your cells is O2 with a double bond in the middle. How about N2? This is one tiny step more tricky. NN and nitrogen is in our 5 valence column. So we get 5. How about we go 2, 4, and I bet that single one gets used for bonding, huh? So let's put it toward the middle. And 2, 4, and I bet that single one gets used for bonding. So let's see, let's make a bond. But both of them are unhappy. They both Venn diagram as having 6, so they both get grabby from the other one. Pick a pair. How about we pick the ends just because I think it looks better? It's not important which ones you pick. I just think it makes it match nicer. And this one goes in here, and this one goes in here somewhere. It doesn't matter which one's top and bottom. We don't know which one it is anyway, do we? Because they're all identical. But now both nitrogen atoms Venn diagram as having 8. This one says I have 8, and this one says I have 8. And the nitrogen that you're breathing right now is a triple bond. And then some kids say, I'm not breathing nitrogen, I breathe oxygen. But Earth's atmosphere is over 60%, I think, nitrogen. So you are breathing nitrogen, you're just not absorbing it for your cells. Actually, you do absorb it a little bit in your blood, but it's not for the purposes of, metabolizing your food like the oxygen is. On number 9, the thing to know is that the multiple C's are in a chain, and I know 2 is not a big chain, so is it really a chain if it's only 2? But they're in a line. And then the H's stick to the C's evenly. So we'll take 3 of them here and stick them to this one. That's sort of even anyway, and then 3 here. And then the H's all have 1 valence, don't they? How about we point that out to carbon, because I bet that's where they need to be aimed for bonding in the future. And then the carbons both bring in 4. So I'm going to take 4 for this one, and I bet I have to complete these bonds. 1, 2, 3, and a 4th one. I bet that has to be aimed at that other carbon. And 1, 2, 3, and 4, and I get a bond there. And the H's think they own the bond, so they are satisfied at 2 valence. And the carbons think they own all the bonds they're touching, so they're satisfied at 8 valence. Now, I can't do all of them, and I already skipped some, but I'll do 10. C, C, and only 1 H, and only 1 H, and H has 1, and carbon has 4, and so I get 8 more, right? So let's see. 1, 2, and that leaves me 6. 3, 4, and I get 4 more, don't I? Well, if we think about it, we could put them at the top, but then we get 2, 4, 6. And if you did that already, it's fine. You can always just erase, right? But if we think ahead a little bit, maybe we can see that's not going to work. If I put 2 here and 2 here, it's not going to work, and I'm just going to have to erase them. So how about we think ahead a little bit and say, I'm going to have to put them here, and it's a triple bond. And that's acetylene for all you people who have seen somebody weld with a gas torch and an acetylene torch. How about we go to, well, I'll just make a note here. This one actually is in that order. And how about we go to cyanide ion? This stuff is incredibly poisonous in real life. This is the classic spy poison. This stuff will knock you down and put you in a grave. Anyway, here's my point. We have C and N. So here's a very key point. This is -1, and that does not mean you have 1 fewer electron. Electrons are negative, so you have 1 extra electron coming to you. I find it easier if I put that extra 1 on either the center atom or the one that has an odd number. And carbon is a 4 valence and nitrogen is a 5. So how about we count this as nitrogen is a 6 this time, because I get a free electron. it stole it from somewhere. We didn't invent it. It's not magic, but it stole it from somewhere. So I get 4 and 6 is 10. So how about something like this? We'll put down something 2, 4, 6, 8, and 10, except that no one's happy. They both feel that they have 6 valence, and so they both get grabby, and they're both going to borrow a pair from each other, and it's a triple bond. And they both have 1 unshared pair on each. Now, the next thing to do, though, to finish this up, and this is the thing I tend to forget, is that we put brackets and the charge is -1, which is basically to say, I know that if you count up the valence here, it's 10, and you would have thought maybe that it's supposed to be 9, but I'm not kidding. There's another one in there, and I didn't make it up. It's really -1 when you look at this diagram. I'm not kidding. It's really, there's an extra electron in there. So how about 18? P goes in the middle. The O's are arrayed around the outside. Oxygen, we know, is 6, and here's a piece of advice. I would put the 6 valence on oxygen and leave them as much as possible. So how about we put 2, 4, 6 on those and leave them? Well, see if we can leave them. Actually, on this one we can. And phosphorus is in my 5 valence column, but I get 3 extras. So how about we say that this time phosphorus is bringing in 8. There are 3 extras somewhere, and it's not illegal to put them where I need them. So how about I say they're on phosphorus this time? And look how many bonds I need to form. 4 bonds, which is going to take how many valence electrons? Well, 8, which is great, because I've got 8 more coming. So 2, 4, 6, 8, and everybody's happy. The only thing left to do is brackets -3. Now, here's one of our real tricks. For carbonate, C goes in the middle. The O's go around the outside. How about we put the 6 valence on oxygen and see where we can get after that? Carbon has 4 valence, but I get 2 extras. So let's count carbon as having 6. And look, I need 3 bonds. And it looks like we're done, but it turns out we're not. 2, 4, 6. Because stop and think a moment. Maybe hit pause. What's the valence count on carbon right now? And it's 6. And carbon is not going to sit there and take it. It's going to get grabby, but here's the weird part. The choices it has to get grabby from, to borrow from, are all equally attractive. These 3 oxygen atoms are in the same position as each other. There's really no way to tell one from the next. And so the carbon's pull for any one pair on any of the oxygens is equal. And so my little phrase is, when the choices are equal, it chooses equally. And what has been proven by some very expensive equipment, I assume, is that it really does choose partially from each. So you would probably say, oh, there's going to be a double bond because now I've been paying attention and we keep borrowing a pair and making it a bond. And that's true. But since there are 3 equal choices, it chooses equally, and we get a 1/3 of a double bond in each direction. Now, I don't have a great way to visualize that. I've still never seen one that really, really explains it. But we do know that this distance with this partial double bond is shorter than the normal single bond distance. And it's shorter all 3 directions too. So it really is a distributed double bond. It's a partial or fractional double bond in all directions. So for my class, what I'm going to say is let's just pick one of them and make a double bond. And for no good reason, I'll just pick this pair on that one, and I'll make a double bond. Now, really, it's 1/3 of a double bond here and here and here. And that is called a resonance structure. And you might recognize the word resonating or resonance. And resonating means like bouncing back and forth, because it used to be thought that it was double bonding here, and then here, and then here, and then here, and so forth and around, back and forth. No one believes that anymore. Like I said, it's been proven that the distances are all shorter, the same in all directions, and they're not changing. So it seems that we're right, and it's a fractional double bond in all directions at the same time. So some classes will have you draw this out 3 times. Once double bonded here, and then here, and then here. For time, effort, and space, I'm going to say let's skip that. And if you will tell me it's a resonance structure, resonance. I'll get this spelled right. I will just allow that to be your clue to me that you know that it's a fractional double bond in all directions, resonance structure. I will point out that that is not renaissance. It's resonating, or they thought it was, so it's a resonance, not renaissance structure. Then some of you have been yelling at me, you forgot something, and you're right, we did not do brackets -2. How about we do 23? All right, one of the classic mistakes, and it does make some sense, but this is a mistake. This is not in a triangle. So I'm going to do this wrong for a moment, and I get kids doing this. And what is a little bit annoying is that I purposely say that is not right. And yet I get a couple quizzes every year where that's the answer given. That is not correct. They are sort of in a line. Now the exact shape we'll leave till another day, but they are not in a triangle connected in all directions. So oxygen, you might remember now, has 6 valence electrons. So how about we put in 6 and then 6 and then 6 and then see where we get. It's probably easier if you put the 6 and then the 6, and then I got to have 2 bonds at least, right? So there's 2 and 4 from the middle one, and then I get 2 more, so at the top probably. It doesn't really matter. You could put it on the bottom. The end one says I have 8. The end one says I have 8, but the middle one says I have 6. It's going to get grabby, but the choices to grab from are equally attractive. And when the choices are equal, it chooses equally. So what we're going to get is half a double bond in both directions. It doesn't matter which one you pick. I'll pick the right one just because I picked the left one last time. I'm going to pull a pair. I'm going to put it in the middle as a double bond, but really it's half a double bond here and really half here. And by putting it's a resonance structure, I'm going to live with that. I'm telling the reader, you know what? It's really equally distributed both directions. How about 31 NH4? Because even after I said it in class, I had a few kids saying, oh, look, an extra electron. No, it's missing an electron. If it's positive, it has lost a negative electron. And we said the singles go in the middle, and the rest are arrayed around the outside. And the hydrogens have 1 electron, and as we learned, it's almost always best to aim that one at your other atom there. And nitrogen is in your 5 valence column, 3, 4, 5, except it's missing 1, or something is, somewhere we're missing 1. How about we pretend that it's on the nitrogen? And we'll say that nitrogen is bringing in 4 valence electrons. And look how many bonds we have to complete, 4. Well, that's pretty convenient. 1 valence from nitrogen, 2, 3, 4. And you know what? Everybody's happy. And we're done, except to say, oh yeah, it really is positive. I didn't just make a mistake and lose 1. Really, really, it's positive. Another thing I should point out, probably the last thing here, is boron trifluoride. So, turns out boron is a bit of a weak sister. And with only 5 protons, it turns out boron breaks the octet rule. So boron goes in the middle, fluorine, fluorine, fluorine. And if you look it up, fluorine has 7 valence, so 2, 4, 6, 7, 2, 4, 6, 7, 2, 4, 6, 7. And fluorine is left of carbon, so it has 3 valence, which seems like really convenient because you need 3 bonds to be completed. So 1 from boron, 2, 3. And somebody's yelling at me, but you said octet rule, that's 8, and boron only has 6, and you're right. My phrase for it personally is boron gets bullied. Boron does not have the strength to get grabby, and it's going to sit there and take it, and that's it. That's where it ends. But I have kids write this phrase, and I make it part of the actual answer. You have to put this, that it's an octet violation. So you tell me, I know that it's not coming up as an octet rule. I know boron doesn't have 8, but I'm serious about that. I didn't just make a mistake. I know it's an octet violation. I mean it. Okay, and then in that case, of course, you're right. Boron gets bullied. We should do maybe this one, 24, and I'm going to go a little bit faster. Sulfur and 6 fluorines, that's a lot. 5, 6, and fluorine is a 7 valence, so 2, 4, 6, 7. And sulfur is in my 6 valence. You can go look it up, and look how many bonds I have to complete. 6, so 1, 2, 3, 4, 5, 6 from sulfur. And the fluorines are all happy, but if you see how many valence electrons the sulfur has, you have to count all the bonds, and sulfur comes up as a 12, which is very much not 8. So this also is an octet violation, just bigger instead of smaller like the boron. One other thing you might not know, of course, is that for 35, N goes in the middle and the O's go around, and the H is on one of these. Actually, let's continue with 35. So it's tempting to put the H on the N, but that's not the way it is. Not that you would know that, but I'm telling you, it's on one of the oxygens. Just pick one. And it's an interesting point here. Which one? Well, we don't know, and it doesn't really matter because there's no top to a molecule. Is that the top? Or maybe that's the top, or that's the top. So there's no exact top to a molecule. So even if you said it's at the top, that doesn't really have a meaning with the molecule. So I just picked one up there just because I thought it looked good. So let's put in our valence electrons. Hydrogen has 1. Oxygens have 6. So how about 1, 2, 3, 1, 2, 3, 4, 5, 6, and then 2, 4, 6, 2, 4, 6. And nitrogen has 5, and look, we need a bond, so that's 2 of them. Bonds, that's 2 of them, now 4 total. And one more here, so that's 5 total. And it seems like we're done, except that nitrogen is Venn diagramming as a 6 valence, 2, 4, 6. And it's not happy, and it's not boron. It's not going to sit there and take it. It's going to get grabby. And here's the last bit, though. This oxygen is already lending an electron this direction. It's in less of a mood, so to speak, to get borrowed from than these two are. So the N is going to borrow from these, but the choices are equal. So it chooses equally. Which one? Both is the answer. So just to be different, I'm going to borrow from the bottom. It doesn't really matter. Pick one, borrow it in here. But really, it's a distributed double bond. Really, it borrowed from both partially, and there's a partial half double bond here and also here. And to show that you know that's happening, we're going to put resonance structure. And yes, it is -1 for not putting that.